vector Z, and the matrix S is symmetric, positive, definite, right? F is a vector is given on the right hand side. We have to do through 3 steps. The first step we call factorization. We want to factorize the given matrix S into the product U transpose of U. So the main goal for step 1 is to find the upper triangular matrix U. That is the main goal. Step number 2, we say we replace S by the product U transpose U. And then Z is there, F is there. Then we move on to step number 2. So we call U, matrix U times Z, we'll give it a new name. We call it vector Y. So U transpose Y to F. So the objective of step number 2 is to solve for the intermediate unknown vector Y. Okay? Because for this system, the matrix U we already know from step 1. Right? So step number 2 we call forward solution is to find the vector Y. And then after that we go to step 3. We remember we say UZ equal to Y. Alright? And we say the matrix U we already obtained from step 1. The vector Y we already obtained from step number 2. Therefore, you can solve for matrix Z. Right? And then we say among the step 1, step 2, and step 3, step 1 is the most expensive. Step 1 is about 19 or 20 times more expensive than just step 2 and 3. Okay? So in the next slide, we explain how to obtain the matrix U in step 1. You see? So we say the given matrix is equal to U transpose times U. So in this example, we have a 3x3 system, and therefore we have 6 unknowns. Because we have 6 unknowns, we need to have 6 equations. So we multiply these two, and then we equate to the left-hand side. Right? So that's how we got 6 equations last time. Those are 6 equations. Those 6 equations will help us to solve for the unknown here. But remember, those 6 unknowns we can do in 2 different ways. We can do row by row by row factorization order, or could be column by column by column. Okay? And another thing we said is, because this matrix in real life can be very, very big, we don't have enough computer memory to store this big matrix and also another big matrix here. So because of that, as soon as we compute the unknown U, we will override on the original location to save the computer memory. Huh? So that is for a 3x3. And then last time, we also say, what happens if the matrix getting bigger? So we say if the matrix is getting bigger, then we have the general equation 4 and 5. Equation 4 can help you to find out the diagonal term. Equation 5 will help you to find out the off-diagonal term. Okay? And because you remember, we have a square root operation, and that's why we require the matrix must be symmetric, positive, definite. Because if it is not positive, then you take the square root of a negative and we have a problem. Okay? And then, so that is the story we have last time. And another thing is, if you want to calculate U5, 7, you need to know column 5, column 7, column 5, column 7. Now, the most important thing about this formula is about this summation of the product. This is the most important thing. So, this operation, U15, U17, U25, U7, it means you talk about column 5, column 7, and you say this times this, plus this times this, plus this times this, right? And that means It's just like the dot product of the two vectors. Right? Because column 5, you just think like a vector. Column 7 is like a vector. And then when you say this times this plus this times this, it's just like a dot product of the two vectors. Okay? Now, last time I also say very quickly that we have 3 loops, 3 nested loops. You see? That's why it is expensive. The first loop with the index j, to make sure that you consider every column. And then, assuming we pay attention to, let's say, a typical column, like column 7, for example. So in column 7, you have the unknown U17, U27, U37, blah, blah, blah. You have a lot of unknown. And that's why you have the second loop. Go from 1 to 7, J7. You see? So that's why you need the second loop, because you have a lot of unknown. And then among the unknown, U17, U27, U37, we just pick up a typical guy, like this guy right here, U47. But if you want to calculate U47, that means you need to know column 4 and column 7. Remember? So you need to have another loop. Last time I explained to you. So because we have 3 nested loops here, that's why it is very expensive. So that's what we said last time. Now today we will be to the new material. Today we talk about the new material. So let me talk about, let's say, page 43. Yeah, let's take a look at on page 43. So we go to page 43. Let's go to page 43. Almost there. Okay. Page 42, 43 is the detail about the so-called forward solution phase. Remember step number 2? Step number 2, as you remember, in step number 2, we have U transpose times Y equal to F, right? So in the long form, U transpose look like this. Because remember, U is an upper triangular, so the U transpose is a lower triangular. Vector Y is here, F is here. Now remember, everything about this matrix you already knew from step number 1. This vector F is given. So the objective of the forward solution is to find out this unknown vector. Okay? As you can see, you look at the first equation, it says U11 times Y1 plus 0 equal to F1. This is what you got. So from this equation, you can solve for Y1. Then from the second equation, you have U12 times Y1 plus U22 times Y2 plus 0 equal to F2. That is this equation, right? And from this equation, you can solve for Y2. And so on, so on, so on, right? So for the third equation, right here, you have what? U13 times Y1 plus U23 times Y2 plus U33 times Y3 equal to F3. And then from that, you can solve for Y3. Now, after you have a formula for Y1, Y2, Y3, you have noticed that the formula getting longer and longer and longer. You see here you have only one term on the top. Yeah? Now, here you have 2 terms. Here you have 3 terms. So the formula getting longer and longer. And because of that, we can obtain easily a general formula. It looks like this. This is a general formula. Okay? So like for example, if you let J equal to 3, J equal to 3, then this formula will become this formula. And let's agree. If you let j equal to 2, then this formula will become that formula. Is that clear? Is that okay? Now, so let's take a look at this formula. Can you tell me, just by looking at this formula, okay? Suppose j equal to 3. Suppose j equal to 3. That means this summation, I go from what? From 1 to 2. Right? So that means you're supposed to have 2 products in there. And that's exactly here, see? One product, another product. Now, what happens when j equal to 1? Well, when j equal to 1, I go from 1 to 0. That's not possible, right? So what does that mean? That means just forget about this. Then y1 equal to f1 over u11. That becomes this one. So now let me ask you this question. This is the step number 2. Can somebody here tell me why step 2 costs less than step 1? What is the reason? I give you some hint. Remember, step 1 is expensive because you have 3 nested loops. Remember that? By looking at this formula, can someone here tell me how many loops you need to have? How many do loops you need to have? Just by looking at the formula.
2 loops.
2 loops. Why? Because the first loop, you have to make sure that you cover the unknown is y1, y2, y3, right? So the first thing you need is to have a loop so that you can calculate y1, y2, y3. Do you agree? So the first loop, to make sure that you will cover all the unknown. But for each value of j, you need to have another loop, the second loop, for the index I. Is that clear? Right? So like for example, when you write a code, you say, do j go from 1 to up to n. That is the first loop. But for each j, you need to have another loop for the index I. Is that clear? And that's why for the forward solution, step number 2, you only have 2 nested loops instead of 3 nested loops like step 1. That's why step 2 is very cheap. It doesn't cost much time. Is that clear? If you don't understand, feel free to ask me and I'll be more than happy to explain again. So I have 2 loops. Now, let me show you a little bit more. Suppose you want to write a computer code. It's very simple. You see? The first loop is the first loop. You have to relate to the index j. Remember? y1, y2, y3, blah, 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 yj. You see? That's j, the first loop. For each j, you need to have another loop for the index I. Go from 1 to j minus 1. See, that's why you have 2 loops. And that's why it is not expensive. Okay? But to find out the factorized matrix U, step 1, you have 3 loops. That's why it costs a lot more. So that is the so-called step number 2, forward solution. You want? That's true, right? So remember, the main thing is this. We want to solve A, x equal to b. So step 1, you say A equal to u transpose times u. And the objective to type is u. Step 2, we say A equal to u transpose u, x equal to b, u times x, you replace by the vector y. So step 2, you want to solve for y. Remember that? And then step 3, we say ux equal to y. Ux equal to y. And we will solve for x. right? So to find out this u, you need to have 3 loops. Okay? To find for the vector y in step 2, we need to have only 2 loops. You see, right? I just said to you. And remember now, in the terminology, step 1, to find out this guy u, you call it is a factorized matrix. Factorized matrix u. Factorize. Step 2, we call forward solution. Forward solution. Step 3 is backward. So I already discussed step 2, right? We just finished it, remember? So now let's talk about step 3. Step 3. Now, remember in step 3, do you know the matrix U? Yes, because we already did step 1. Do you know the vector Y? Yes, because we just finished step 2. That's why we can solve for X, right? Let me show you the details. The detail is here. Step 3. Here you go, right here. Very clear, let me show it. See, look at step 3. U is an upper triangular matrix, upper. That's why it looks like this. Okay, and then Z is unknown, and then Y is here. So now for this one, of course, you have to look at the last equation. Right? Look at the last equation. What does it say? 0 plus 0 plus 0 plus U4 4 Z4 equal to Y4. So from that you can solve for Z4. Agree? And then you go backward. Look at the third equation. 0 plus 0 U33 times Z3 plus U34 Z4 equal to Y3. From that you can solve for Z3. Is that clear? Then you go backward. So the general formula is here. You see, you solve for Z3, then you solve for Z2, then you go backward, solve for Z1, and this is the general formula. Agree? Now, of course, if you let J equal to 3, then this formula becomes that. When J equal to 2, this formula becomes this. Okay? And when J equal to 1, this formula becomes this. Alright? Now, let me ask you another question. Just by looking at this equation, can you tell me how many loops you need to have?
1.
How many?
1.
Okay, that's your idea. I don't say you are wrong, I don't say you are right. I just say, okay, how about you? How many loops? Just by looking at this equation. Just tell me. 2. See, because the first loop, you make sure that you will take care of all the unknown, like Z3, Z2, Z1, or in general, Zj. So you need to have the first loop to make sure that it will take care of all the unknown. Right? The first loop you need is about the index j. But for each of the index j, you have another loop with the index I. You see? That's why you need to have second loop, 2 loops also. So here, step 2, you need 2 loops. Step number 3, you also need 2 loops. And that's why step number 2 and step number 3 combined together, it is still very, very cheap. that tree have 3 loops, very expensive. Is that clear? Make sure you understand. Now let me tell you another secret. Very important, very secret. So now you understand the procedure, right? If I give you a matrix A, all right, matrix A, which is symmetric, positive, definite, then of course you can use this procedure, which we call Cholesky, right? Cholesky method. Okay? So here's my question. If I give you a matrix A, symmetric, positive, definite, I give you the right-hand side vector B. Of course, you can follow step 1, 2, 3 to get the solution. Am I right? But actually, in reality, in real life, nobody do that. We have to do some special trick. And let me share that special trick or special secret for you. Okay? So for that, you need to go to page. Okay. So let me go back. Let's go back to page 20. Something very important. Yes, very, very important. Let me show you ready. Yeah, this is a very important. What page is that? Page 18. Okay, page 18, very important. I will explain to you. See, this is very important. Have you noticed in this matrix is given to you, right? This matrix S, it's just like a matrix A, okay? It's given to you. Now, do you agree with me? This matrix is symmetrical, right? That's why I don't show you this part. But pay attention. You have a lot of zero. See that? You have a lot of zero. Now, let me draw the profile like this. See that? Now, if you look at that picture, what does it look like? It looks like when you drive your car on the street at night, it looks like those are like a high-rise building. Do you understand? Like a high-rise building. It's just like here is like the roof of the building, right? So that's why when I draw a picture like this, we call the profile. Profile of a matrix. Okay? Now, you see, take a look. What is this column? Can you tell me what is this column? That is column 5, right? Column 5, you see there's a 3 0 here, 3 0. They are above the roof of the building. Am I right? Take a look. You see, this is column 5. They have 3 0 above the roof of the building, right? So, let me ask this. What is this location? Row 3, column 5. Am I right? Row 3, column 5. So let me write out. Well, this is very important. Okay. So row 3, column 5. So if I ask you, U3, 5 equal to what? Of course, you will say it is equal to what? Remember the picture? It will be equal to S or A, same thing, at the same location, 3, 5, minus summation of U, K, I, U, K, J, divided by UII. Remember that? Okay. Now, in this example, can you tell me what is the value of this guy? What is the value? What?
Zero.
Zero. You see? Of course, zero. Okay? So this is zero. So according to this formula, if you use this formula, of course you will figure out U3, 5 equal to some value. You agree? Agree? Here's my question. Is this value equal to 0 or non-zero? I don't really care about the actual value. The actual value is not important for me right now. The actual value may be 3.6, maybe minus 2.8, I don't care. Only I ask you is, will this value 0 or non-zero? What do you say?
It's different from zero.
Well, for this example, this guy will be 0. I'll tell you why. You see, this value is 0, everybody agreed, right? So, suppose this is the summation of the product. Remember? This times this plus this times this, right? So if the summation of the product is 0, then this guy will be what? 0. Do you agree? But if the summation of this product is not 0, then this guy will be non-zero. Do you agree? All right. Now, let me give you a hint. If you want to calculate U35, remember I told you you need to take a look at column 3 and column 5 to figure out this product, right? So let's take a look. This is column 3. This is column 3, okay? And this is column 5. Agree? By looking at column 3 and looking at column 5, can you tell me what is this product? 0 or non-zero? 0. Why? Because look column 3, column 5. This times this. 0 times 0 is 0, right? Plus this times that. Still 0. Do you understand? You understand? So because this guy is not 0, therefore because this guy is 0. 0. Because this guy is 0, therefore this guy is 0. Now, there was a very famous professor in the USA. His name is MIT Professor